Let's start with this topic, perpendicular and parallel axis theorem. Complete stronger plussing. So let's start with part 1. Why do we even need these theorems? You already know about how to find moment of inertia of a sphere or shell about its diameter. We did it in some other video, so that an axis passing through the center, the diameter. But exam questions constantly ask for MOI about different axes, the tangent, an edge, a parallel line somewhere else. Instead of redoing the whole integration every time, success find two shortcut theorems, simple formulas that let you jump from MOI about one easy axis to MOI about any other axis without any new integration. That's the entire. Let's start with a picture in your head. Imagine you're spinning a coin on a table. It's easy to spin around its center like a wheel on an axis. That's the axis you already know how to handle. But what if someone asks, what if you spin the coin around its head instead like it's stuck on a pin at the rim? That's completely different axis, and normally to find a more about a new axis, you'd have to redo a whole integration from scratch. New limits, new setup, same thing. The whole point of today's lesson, two shortcut formulas that let you jump from I know MOI about easy axis center straight to I know MOI about this new axis with zero new integration. Just plug into a formula. Let's build up to them slowly. 147. Okay, so part 2, quick recap. What even is moment of inertia? Before axis, let's make sure this part is rock solid. Moment of inertia is just the number that tells you how hard is it to spin this object. Two things affect it: how much mass there is and how far that mass sits from the spinning axis. And distance matters a lot, not just a little, it's squared. So mass that's twice as far away contributes 4 times as much resistance to spinning. That's why figure skaters spin faster when they pull their arms in, less mass from the axis. So the formula for moment of inertia is this: mr squared summation, and the integration form is r squared dm. Just means take every tiny piece of mass dm in the object and multiply it by its distance squared from the distance from axis squared, and add all those up. That's it. That's the whole building block we need. Let's move on to the theorem 1. So theorem 1, the perpendicular axis theorem. Part 3, what it says in plain English. First, picture a flat object like CD, a coin, a flat washer, something thin with basically zero thickness. This is called lamina. Now imagine 3 axes all crossing through the same point. One axis lying flat, going left right, call it X. One axis lying flat, going front and back, call it Y. One axis sticking straight up out of the flat object like a skewer through the center of the coin, call it Z. So the theorem says something almost surprisingly simple. The MOI about the vertical skewer Z, MOI about Z equals MOI about the left right axis plus the MOI about the front back axis. Okay, so IZ, moment of inertia for along Z axis, equal moment of inertia along X axis plus moment of inertia along Y axis. One important catch: this only works for flat, thin objects, not a solid ball, not a thick cylinder. Only things like discs, rings, flat plates. This trips people up in exams, so lock it in now. Flat objects only. Part 4, let's prove it slowly. We are going to prove this using nothing but distance and the definition from part 2. No new tools. Step 1, set the scene. Picture a flat coin lying flat on a table, like a piece of paper on your desk. Draw 2 lines on the paper crossing at the center, one going left right, one going up down on the paper. Now imagine the third axis poking straight up out of the paper through that same center point, that's Z. Step 2, pick one tiny piece of the coin. Let's zoom into just one tiny speck of mass on the coin, call it dm. Its location on the flat paper can be described with two numbers: how far it is, like x, and how far up it is, how far right it is, how far up it is. So x and y. Step 3 is how far is this speck from the vertical skewer z-axis. This is just everyday distance, like using a ruler on a map. This is just everyday distance, like using a ruler on a map. If a point is x units right and y units up from the center, its straight line distance from the center is given by good old Pythagoras theorem. Plug into our MY formula. So now r squared is basically this squared now. Step 5, split it into two separate pieces. Here's a simple math move. When you are integrating a sum, you can just integrate each part separately and add the results. Like saying the total cost of apples plus oranges equals to cost of apples plus cost of oranges, calculated separately. So here's the aha moment. Step 6. Now look closely at y square dm. Ask yourself, what does this represent? Think about the x-axis, the left-right line on our paper. How far is our speck mass from that line? Think about the x-axis. How far is that speck of mass from that line? Well, only the up and down distance matters here, which is y. So the distance from x-axis is just y. So this means that this is literally the definition of my about the x-axis. And by the same logic, flipped, this is the distance from the y-axis. So we have this equals to this, put it together, we have it proved, done. That's the full proof. And notice, we didn't need anything fancy, just Pythagoras and recognizing what each piece meant. This was pretty simple actually. So theorem 2, the parallel axis theorem, what it says, plain English first. This one answers a lot of questions. This one answers a different question. I know the MOI about an axis through the very center of an object. What if I move that axis sideways, keeping it pointing the same direction, just shift it over? Like instead of spinning the coin through its center, now spin it around the axis that's shifted 2 centimeter to this side, still pointing the same way, still vertical, just moved. So new MOI equals MOI about the center plus mass times distance shifted squared. So mass times distance squared plus mass times distance shifted squared. So this new moment of inertia for that axis equals moment of inertia from the center of mass plus md square. So here ICM means moment of inertia about the axis through the center of mass, m is the total mass, and d is how far you shifted the axis. D is how far you shifted the axis. Good news. Unlike the last theorem, this one works for any shape, flat, solid, whatever, no restrictions. Part 6, let's prove it slowly, one step at a time. Okay, so let's prove it slowly, one step at a time. Step 1 is set up two axes. Let's say the center of mass of our object sits at a point we'll call O. Think of this as the origin, like 0 point on a graph. That's an axis through O. There's an axis through O pointing straight up. Now somewhere else at distance d away, there's a second axis parallel to the first one, same direction, just shifted. Let's call that point A. Pick a tiny speck of mass again, just like before. Take one tiny piece dm somewhere in the object at position xy, measured from the center O. Distance from the center axis. Now distance from the center axis equals this, same as before. Distance from the new shifted axis. This is the only new idea in this whole proof. Since the new axis is shifted d by d, we measure distance from a point a equals d comma 0 instead of this O. So this a is d distance apart from like one of its coordinate. Okay, so the distance formula becomes um this x minus d squared plus y squared. So because this is already plus d, our x is already plus d, so to neutralize it, I guess we subtract d again, and then we have the new distance formula. We just subtracted d from x coordinate since we shifted along the x direction. Write the MOI about this new axis. So the MOI about this new axis equals this. Expand the bracket. Just algebra here. Expand x minus d the whole square. The same way you'd expand these identities. So using the identity, we can expand this thing. So now the moment of inertia equals this. Split into 4 separate pieces for 4 terms. Let's tackle these one at a time slowly. So piece 1 to 4 together. X squared plus y squared dm. X squared plus y squared dm. We write it together. Now x squared plus y squared was ro squared. That's just the MOI about the center, which is this moment of inertia about the center by definition. So this piece 2 is this 2x dm. Here's a nice trick. D never changes. It's a fixed shift distance, so we can pull it outside the integral, like pulling a constant out of the sum. So 2D is out now. XDM. Now here's the key physics fact to know. Integration of XDM tells you the location of the center of mass multiplied by the total mass. But how? I did not understand this part. X, this tells you the location of the center of mass multiplied by the total mass. But wait, we deliberately measured everything from the center of mass. So the center of mass's own position measured from itself is exactly 0. So now this part equals 0. We are only left with 2D. This whole piece vanishes. Poof. Piece 3 d square dm. Now d square is also constant, so pull it out. We have this. We can write 1 in here, I guess. So now d square times m, because adding up all the tiny dm pieces just gives you the total mass. Combine everything. Now we have our formula. That's the full proof. The whole trick was that middle term vanishing, and it only vanishes because we measured from the center of mass. So quick side by side summary. Perpendicular axis theorem works for only on flat or thin objects only, and the parallel axis theorem works for any object, any shape. The formula for this is this and this formula, but it connects 3 axes crossing at one point, and this is about 2 parallel axes, one through center of mass. Take a breath there. That's the full theory full done. Everything from here is just using what we built. We will see this part again, this part 2 of XDM. Copy, but for now let's just move on. So everything from here is just using what we built. Part 8, one worked example, nice and slow. Question is to find the MOI of a solid sphere about a line just touching its surface, a tangent. So MOI of a solid sphere about a line just touching its surface, a tangent. So that tangent is parallel to the center of mass axis, whatever. So, but we already know a standard result. MOI of a solid sphere about its diameter through the center is this formula. We already did it in some other video. You can actually memorize this formula. This is going to be very useful. Step 1 is to picture the geometry. A tangent line touches the sphere at just one point on the surface. It's parallel to the diameter, just pushed outwards by exactly one radius. So identify the shift distance. So now our distances are plug into the parallel axis theorem. Here we have our formula. Applying it, we get this. Add the fractions carefully. To add these, rewrite mr squared as a fraction with denominator 5. Now we have 7.5 mr squared. No new integration, just one known result plus one formula. That's the power of these theorems. Recap: we did the proof for perpendicular axis and proof for parallel axis. Then we did one numerical, but I did not understand this piece. I did not understand this piece from theorem 2. Explain again. Okay, zooming into that, into just that piece. Let's break this into two separate questions. Question 1: why can we pull d out of the integral? That I got. But question B: why does this actually mean? What does this actually mean, and why is it 0? I did not understood this part, so shall I skip this? You can read if you want to, but I'm not going to read right now. Okay, so question B: what is XDM really? This is the part that needs a slow analogy. Think about a seesaw. That is the part that needs a slow analogy. Think about a seesaw. Imagine a long plank with several kids sitting on it at different spots. Some kids are heavier, some lighter, some sit far from the middle, some close. There is a special balancing point on that seesaw. The point where if you put a support directly underneath it, the whole thing balances perfectly. That balancing point is exactly what we mean by center of mass. Now, here's a connection to our integral. The quantity, this integration of xdm, is basically a mathematical way of describing how lopsided the mass distribution is. What? How lopsided the mass distribution is? It's adding up every tiny mass piece multiplied by how far it is from wherever you chose to put your origin, your 0 point, your ruler's starting mark. So that's the known formula. Connecting this to center of mass position is the key. I still did not understand what the hell. Let me just uh, let's slow it down on this one piece. This is honestly the trickiest single step in the whole proof. So let's isolate it completely and build it from scratch. Step back. What does center of mass actually mean? Before we touch the integral, let's nail the idea of something physical. Imagine a seesaw. This is a chair, not a seesaw, anyways. Where you have got a bunch of kids sitting at different spots along it. Some heavy, some light. That's exactly okay. So you can read this. Here's the intuitive rule for how that balance point is calculated. You take every kid's weight multiplied by how far they are from some reference point, and add all of those up and divide by total weight. That gives you the position for the balance point. Now let's write that as a formula. If we have a bunch of separate masses m1, m2, m3 sitting at position x1, x2, x3 positions, so we are taking m1, x1, m2, x2, we are adding those up, summation of mi xi upon the total mass m, capital M. This is just weighted average position weighted by mass. Now for a solid object, not separate chunks but continuous blob of matter, we don't have discrete m1, m2, we have infinitely many tiny pieces of mass, each called dm. So the summation turns into integration integral. So now this mxi becomes, this m mass becomes dm and x is same. Okay, so this is the key formula. Read it in words. Add up every tiny mass piece into its position, then divide by total mass and you get the balance point. Okay, so now rearrange this. This is the part we actually use. Multiply both sides by m. So now xdm equals m dot xcm. In plain words, this is just asking where is the balance point of this object weighted by mass times the total mass. It's the mathematical machinery for locating the center of mass. Mathematical It's the mathematical machinery for locating the center of mass. Now, why is it 0 in our proof? Go back to step 6, step 1 of parallel axis proof. We made a deliberate choice. We placed our origin O exactly at the center of mass of the object. That was our setup from very start. Remember, we said let's the center of mass sit at point O. So now ask if we measure the position of center of mass using the center of mass itself, a reference point, wait. So now ask if we measure the position of center of mass using the center of mass itself as our point, reference point, 0 point, what do we get? Think about it like this. If you are standing exactly at your own house and someone asks, how far are you from your house? The answer is obviously 0. You can't be any distance away from yourself. Same idea. So the XCM, the center of mass, because 0, because we measured everything from the center of mass. So plugging this into our formula, we just have 0. What did we calculate from the center of mass? So we are the position of sitting at this, the position of center of mass is this. Part 6, step 1. Anyways, I'm still a little confused. I don't know why. Okay, so we measured everything from the center of mass itself. So the center of mass. What is this XCM, by the way? What exactly is this XCM? Is it distance from the center of mass? If I ask where is this, would you point somewhere like center of mass balance point? Okay, so now this is a good explanation for that. So a concrete example, no formulas yet. Let's use two coins on a ruler. Coin A is mass 2 kg sitting at 1 centimeter mark, and coin B mass 2 kg sitting at 5 centimeter mark. Since both coins weigh the same, the balance point is exactly in the middle, 3 centimeter mark. You could balance a ruler on your finger right at 3 centimeter and it wouldn't tip either way. So measuring from wherever our ruler 0 happens to be, the center of mass is at point 3. Now step 2, now let's move our ruler's 0 mark. Here's the important part. The ruler's 0 isn't some fixed law of the universe. It's just wherever we decide to start counting. We can slide the whole ruler left or right, relabeling the marks, and the coins don't move an inch, only the numbers change. Now let's slide the ruler so that the 3 centimeter mark now becomes the new 0. Now relabel. Coin A, which was at 1 centimeter, is now at -2, and coin B, which was at 5, is now at +2. So where is the center of mass now using the new numbers? Now we calculate the center of mass using the new coordinates. It would be 0. So look at that. It came out to 0 automatically using the actual formula, not because we assumed it. The math just gave us 0. Why did that happen? The real aha moment. Think about the center of mass formula. It takes each mass, multiply z by its position, adds them up. If a chunk of mass sits left of the balance point, it contributes a negative number, and if a chunk of mass sits right of the balance point, it contributes positive number. And because the balance point is by definition the spot where leftward pull and rightward pull perfectly cancel, those positive and negative contributions always cancel out exactly, no matter what masses or positions you start with. That's the whole definition of the balance point. It's one spot where everything cancels. So bringing it back to the proof, that is why in the parallel axis theorem, when we said let the origin be 0, be the origin O be at the center of mass, we did exactly what we just did with the ruler. We shifted our 0 mark to set right at the balance point. And just like our coin example, the moment you do that, we get this equals to 0, and that's it. I hope everything is clear to you too.